Hi guys, welcome back to mathematics0110. In this video, I'm going to show you how to graph using calculus. What's nice about this process for graphing is that it's not like graphing a parabola by putting it into vertex form, or graphing a line by identifying it in the form y equals mx plus b, or any of those other graphing strategies that are based on fitting a type of function into a prototype and then looking at the attributes of the function in terms of that prototype, like where's the vertex, where's the point of intercept with the y-axis, so where's the y-intercept. All those types of graphing only allow you to graph one particular type of function. Using calculus, you can graph any type of function and capture its key features without fear of missing something like a maximum, a minimum, or any other point of interest. The process for doing this is going to involve multiple steps. So this looks fairly horrifying. You look at this as a to-do list or as a grocery list of things that you need to do in order to make a sketch. It is fairly daunting. The first thing is you have to identify the domain. When you make a sketch, you have to know, well, what x values am I looking at anyway? Don't bother trying to find out how the function is behaving in a region where it doesn't exist. You will, at some point, maybe near the beginning or maybe at the end, it doesn't matter, need to determine if the function has any horizontal asymptotes. So what happens to the y value when x goes to plus or minus infinity? You'll also need to find out if the function has vertical asymptotes, and hopefully that will be connected to your process for finding max and min, or sorry, for finding the domain. So an asymptote is a place where the function's y value explodes to plus infinity or minus infinity. So that may happen when the denominator of the expression goes to 0. It may happen when the argument of the log function goes to 0 plus, so 0 from the right. And there's other ways you can get vertical asymptotes as well, but those are the two that we will worry about. Then, once you have those key features, the domain, the existence of horizontal and vertical asymptotes, you can start looking for other features like local max and local min that will require you to take the first derivative, do an increasing decreasing test, or a second derivative test to find if any of those results in critical points are maxima or minima. Then you'll need to look for points of inflection. To do that, you'll check for regions of concave up and concave down. And then at locations where the concavity switches, those are points of inflection. Both for the max and min and for the points of inflection, once you get the x values where these features happen, you'll need to get the corresponding y values. That'll give you some xy pairs to pin down on the graph. So thinking back to when you were a small kid and you were doing connect the dots, you had these diagrams that were numbered. So you had the diagram that was the first point, and that was the second point, and that was the third point. What you did back then as a small kid was you took your pencil crayon, and you connected those with straight lines. Well, what we're going to do is kind of like that. We're going to take our special points, our max and min, our points of inflection, and we're going to connect the dots, but we're not going to use straight lines, we're going to use curves. And there's only going to be 3 different types of curves, either straight line curves, which we frankly won't have because we know how to graph straight lines, or we'll have curves that are, I have to take that back, there's 4. There's a curve that looks like this for a function that's increasing and concave up. There's a curve that looks like this for a function that is increasing and concave down. We also have decreasing concave up like this, and decreasing concave down like that. So we'll connect the dots with one of those 4 shapes. We may also want some more dots. We may want to find intercepts. We may want just to plug in some random x values and get the corresponding y values out and put those down too to help us when we do our connect the dot process. So we'll pencil all those in and connect them, and that'll give us our sketch. First example, polynomial. You may have a competing approach for how to graph this already, but abandon that because this is going to be better. Now, in this example, the process is spelled out for you. It doesn't just say sketch the function. It's asking for each of the pieces to be done in particular order. So for this problem, it's saying find the intervals where f of x is increasing and the intervals where f of x is decreasing. Increasing and decreasing are properties of the first derivative. If the first derivative is positive, it means the function is increasing. If the first derivative is negative, it means that the function is decreasing. So what I'm going to do is I'm going to take the first derivative, and we get 6x squared minus 12x minus 18. Then we want to check where's the first derivative equal to 0. That will tell us where to break up the number line to probe increasing and to probe where the derivative is positive or negative, and then that will tell us where the function switches from increasing to decreasing, or vice versa. Okay, so setting that first derivative to 0, we need to common factor. I'm going to common factor a 6 out, so we have x squared minus 2x minus 3. And then we have to factor that using a product and sum method. So two brackets, each leading with an x, and we want mystery numbers and multiply together to give you negative 3, and add together to give you negative 2, and the answers are negative 3 and positive 1. So they multiply to give you negative 3, add to give you negative 2. Those work. This gives us two x values. X is 3 or x is negative 1. Those are the two ways in which you can make left-hand side equal right-hand side, making either of those brackets equal 0. So then the entire expression on the right is equal to 0, which matches what is on the left. Now we have to make a number line. I'm going to cut the number line. Oh, and it doesn't ask us to do this, but it's important to think about domain. The x values that you can plug into a polynomial is everything. The domain of a polynomial is all real numbers from minus infinity to positive infinity, so that's my number line. I'm going to cut this number line at those two x values that we found at negative 1 and positive 3. This gives us three different regions we have to check. We have the region from minus infinity to minus 1. We have to pick any number inside that region as a test value. I'm going to choose a test value of negative 2 in that first region. Anything that's less than negative 1 will work. Pick negative 2. And what we do with it is we plug it into the first derivative. And it's easier to plug it into the factored form. So f prime, and I'll do it over on the left-hand side because there's some space over there. F prime at negative 2 is 6 times negative 2 minus 3, so negative 5, times negative 2 plus 1, so negative 1. You can multiply them all a little if you want, but all that matters is this positive or is this negative? Positive 6, negative 5, negative 1, two negatives, positive, multiply to give you a positive. This means it is increasing inside that first region. Increasing on the interval from minus infinity to minus 1. I'm going to indicate that with an up arrow. Now we choose the next test value, any number between negative 1 and positive 3. I'm going to choose, I'm going to choose positive 1. You can pick 2 if you want, or you can pick 0, or you can pick 3 over 2, any number. Then I'm going to plug that in to the first derivative, so f prime of positive 1. I have 6 times 1 minus 3, so negative 2. 1 plus 1, positive 2. I get a negative. This means it is decreasing on the interval from minus 1 up to 3. So these intervals, the breakpoints, that's where the derivative is equal to 0. 0 is neither a negative nor a positive number. Okay, and then I might as well put the arrow, the down arrow for that one. And we have one more region. We need to check what is the function doing from 3 to infinity. We need to choose a test value for that region. I'm going to pick 5. You could pick 4 if you want, or 10, makes no difference. F prime of 5, we have 6 times 5 minus 3, which is 2, and then 5 plus 1, which is 6. This is a positive number, and that means it is increasing. On the interval from 3 to infinity. All of these increasing and decreasing descriptions, they refer to the original function f of x. So that's what f of x is doing in those intervals. Okay, part B. Determine the xy coordinates of any local max and min. So from our diagram, from the diagram, we can see that there's a local max at -1. The function's going up and then back down. So local, I should add the word local here, local max at x equals -1. We need the y value. How do we get a y value? Well, we plug the x value back into the original function. Y equals f of -1, which is 2 times -1 to the 3 minus 6 times -1 squared minus 18 times -1 plus 25. This is where I make all my mistakes. -2, -6, plus 18, plus 25. So let's see. I have -8 plus 18, so plus 10. So 10 plus 25, I have 35. So this says max, local max at -1 comma 25. All right. Next, looking at the diagram, we have a spot where the function goes down and then back up, and that's happening at 3. That looks like a minimum. So local min at x equals 3. Now we need the y value at that point. Y equals f of 3. Oh, I don't like this. 2 times 3 to the 3 minus 6 times 3 squared minus 18 times 3 plus 25. Oh, this is not going to be good. 2 times 27, 54, minus 6 times 3, 54. Oh, that's not too bad. Those cancel out. And then 30 plus 24, another 54 plus 25. Something's wrong. Hold on. Oh, minus 54. Plus, that's a minus. Okay, so I have, let's see, so negative 29, I think. You'll have to tell me if there's a mistake in the video and I'll post a correction. So this means we have a min, local min, at 3 comma negative 29. Okay, so that's it for part B. We found the max, we found the min. Part C. Find the intervals where this function is concave up and the intervals where this function is concave down. Concavity is a property of the second derivative. That means we need to find f double prime and do some analysis of it. My camera not focusing right. Okay. So we found the first derivative was 6x squared minus 12x minus 18. Now we need to find the second derivative. So we take the derivative of that, we get 12x minus 12. A function is concave up if its second derivative is positive in a particular region. It's concave down if its second derivative is negative in a particular region. That's the definition of concavity. We want to know where does it switch from one to the other. So we're going to set it equal to 0, as 0 is a number that's between positives and negatives. So 0 is equal to 12. I'm going to common factor 12 out, 12 times x minus 1. There's only one solution here. We have a solution at x equals 1. Okay, next thing we do is we make a number line. Our number line again goes over the domain of this function, which, since it's a polynomial, is minus infinity to infinity. This time we only cut the number line at one spot, at the x coordinate we found, which was 1. We have 2 regions to test. My first test value, any number to the left of -1, I'm going to pick -2. So anything left of 1, doesn't matter. And then to the right, I'm going to pick a different number. I'll use a different color as well. I'm going to pick 3. You could have picked 2, but I'll pick 3. Now we plug in the test values into the second derivative. F double prime at -2. So we have 12 times -3, which is negative. That does not mean decreasing. We're talking about the second derivative. This means concave down. So the second derivative being negative means f of x, the original function, is concave down on that interval, on the interval from -infinity to +1. Now we check the second derivative at the next test value. F double prime at 3. So we have 12 times 3 minus 1, so 12 times 2, which is positive, and that means it's concave up on that interval from 1 to infinity. I'm going to put a little up bowl and a little down bowl to indicate what the shape is inside those two different regions. Part D. Determine the xy coordinates of any points of inflection. Points of inflection are defined as coordinates where the function's concavity switches from one type to the other type. We can see in the diagram that this function switches its concavity at x is equal to 1. So that's the x-coordinate of a point of inflection. So POI, point of inflection at x equals 1. We need the y-coordinate. Y is going to be equal to f of 1. Did I do that already? No, it was f of -1. Okay. So f of 1, that's going to be 2 times 1 to the 3 minus 6 times 1 squared minus 18 times 1 plus 25. So 2 minus 6 minus 18 plus 25. So let's see, is that -1? 2 minus 6, negative, what am I doing? -4 minus 18, so -22. Is that +3? Again, let me know by email if there's a typo, and I'll fix it. Okay, so POI at 1,3. The screaming is a 3-year-old abandoned so I can make a video. He's not, I'm just kidding, he's not abandoned, he's with his sisters, I think. Okay, so that's it for part D. Part E, determine any vertical and horizontal asymptotes of the function. Well, this part's easy for a polynomial. So you have to go into this sometimes preloaded with some type of knowledge, like knowing that a polynomial doesn't have vertical and horizontal asymptotes. Like there's no place where you can divide by 0. And also, if you take the limit to infinity, there's no way you can get a nice number. You can't get like 3 or 7 or 8 if you're taking x to infinity. So, no vertical asymptotes or horizontal asymptotes since f of x is a polynomial. All right. Everything we've done so far has been a review of earlier material inside Chapter 3. This last question, part F, this is the only new thing. It's how do we take all the information that we just collected and put it together to make a sketch. So the first part of this process is going to be to put down the dots for a picture. The dots for us will come from the max at -1, 25 and the min at 3, -29. So -1, 25, that was our max, and 3, -29 was our min. Doesn't have to be perfect, it's just a sketch. So notice that these axis labels, they're very coarse. The distance between the lines is 25 units high. So I'm just estimating what -29 would be. It's probably a bit higher than that, but it doesn't matter. That's our min. And we have another point which is important, and that's the point of inflection at 1, 3. I think it's at 1, 3. I'm going to double check that calculation because I'm paranoid. We have -24 plus 2, so -22. Yeah, I guess it is 3. Okay, so it's very close to 0 at 1, comma 3. Okay. Now we have to see how to connect those dots. It is the case that we have a function that is going up, down, back up. So I'm going to draw those arrows, up, down, back up. So it's going up like this, then it's going down until we hit 3, and then it's going back up. So it has that shape. So that's its increasing decreasing graph, and I'm going to pick a different color and do the concavity graph. It's concave down to the left of 1, concave up to the right of 1. So concave down and then up. So we need to combine the increasing, decreasing, and concave up and concave down information to connect these dots. So the first connection I want to draw is between the max and the POI. Between those 2 points, the function is decreasing and concave down. So decreasing and concave down. Hey, don't do that. Decreasing and concave down looks like that. Now it switches to concave up at x is equal to 1, but it's still decreasing, so it has to be decreasing, concave up. I'll use a different color, even though graphs usually all are one color. It'll make it easier for labeling purposes. So decreasing plus concave up. And the blue was decreasing and concave down. Okay, so we connected the dots, but we have to figure out what's happening to the left and right of those points. To the left of the max, the function is increasing and concave down, so I'm going to draw that. So increasing plus concave down. And it goes down forever. It doesn't come back up because there's no other min off to the left. We know it doesn't curve back up from the non-existence of any other minima. And to the right of that min on the right-hand side, what do we have? It switches to increasing, and it's concave up on that side still. So increasing, concave up looks like this. Increasing plus concave up. And there's our sketch. That's what this cubic function looks like. And it's not perfect, right? The minima has been just, penciled in. It's not exactly there. The POI is not exactly there. Like, its exact coordinate we know, but the sketch doesn't have to be perfect. It's a sketch, not make a work of art. And even art isn't perfect. Okay, and the next example, I'll make a separate video for that.